All right, let's dive right into this explainer. We're talking about the messy, magical, and frankly, absolutely critical world of rare earth elements. You hear about them all the time in the news, right? You're probably holding some right now in your smartphone. But the sheer scientific drama behind how they were discovered, separated, and actually used, well, it's something else entirely. To really grasp how these elements shape our modern world, we're going to follow a pretty clear roadmap today. We'll start with the rare earth puzzle, then move into spreading and the separation. After that, we'll explore cerium's role in forging extreme alloys, see how these elements actually control the nuclear chain, and finally, we'll look at the green future of extraction. Part 1. The rare earth puzzle, defining the boundary. We really have to start with a historical scientific mystery here. Where exactly do the rare earths end on the periodic table? Because for decades, chemists literally did not know. Back in 1911, a French chemist named Georges Urbain confidently claimed that element 72 was the final rare earth. He called it celtium. But science thrives on testing claims. By 1914, Henry Moseley uses X-ray spectrometry to map out the rare earth series, and he shows it occupies exactly 15 spaces, from lanthanum to lutetium. But the ultimate plot twist? That came from the legendary Niels Bohr. Bohr realized the rare earth series exists because a specific internal electron shell, the 4F shell, is filling up. He theoretically calculated that this filling process finishes at element 71, lutetium, meaning Bohr predicted element 72 wouldn't be a rare earth at all. It would actually behave like the transition metal zirconium. And following that brilliant theoretical prediction, George D. Hevesy and Dirk Koster analyzed zirconium ores in 1923, and bam, they discovered hafnium. That definitively proved element 72 wasn't a rare earth, finally closing the boundary of the series. Moving on to part 2, spreading and the separation, unleashing the elements. Okay, so once scientists finally knew what the rare earths actually were, the next monumental challenge was figuring out how to separate them from one another. And that brings us to Frank Spedding. His monumental legacy is immortalized in the Handbook on the Physics and Chemistry of Rare Earths. Spedding was the guy who took rare earths from being these frustrating microscopic laboratory curiosities and turned them into something available on a macro scale. And he had to do it under the incredible high-stakes pressure of World War II. His breakthrough wasn't just some theoretical exercise. It was a desperately needed, step-by-step chemical innovation. During the Manhattan Project, scientists building the first nuclear reactors realized they had a terrifying problem. As uranium fissioned, it created these radioactive rare earth impurities. And these impurities acted as neutron poisons, meaning they absorb neutrons and threatened to completely choke out the nuclear chain reaction. So Spedding and his team at the Ames laboratory were immediately tasked with getting those dangerous rare earths out of there. By developing a revolutionary ion exchange elution technique, they finally figured out how to separate incredibly similar adjacent rare earths in massive quantities, literally saving the day. Which leads us to part 3, cerium, forging extreme alloys. Because once Spedding successfully separated these elements, we could finally start harnessing their individual superpowers. To understand cerium's role in modern engineering, we gotta talk about dispersion strengthening. This is a metallurgical mechanism where fine dispersed particles, specifically cerium oxide in this case, are formed inside an alloy's matrix. Think of it kind of like an internal heat shield and skeleton for metals. It makes the overall material significantly more robust and highly resistant to extreme temperatures. And this perfectly illustrates how just a dash of cerium can transform ordinary metals into extreme military hardware, stuff that can survive blazing temperatures and piercing impacts. Take the ZT3 cast titanium alloy used in jet aero-engine compressor cases. By adding cerium, this metal keeps its structural strength at a blazing 500 degrees Celsius. Cerium acts like a cleaner. It reinforces the grain boundaries of the alloy and actually changes how it fractures, so it breaks through the grains rather than between them, massively preventing failure. We also see cerium in heat-resistant steels, boosting their lifespan by up to 5 times at 1,000 degrees. Oh, and in a totally different application, mish-metal magnesium alloys leverage cerium's pyrophoric nature, meaning it sparks and burns easily, to create artillery shell liners that burn with intense heat upon impact. Pretty wild. All right, part 4, controlling the nuclear chain, poisons and modifiers. But rare earths do far more than just reinforce steel. They actually hold the power to control the fundamental forces of a nuclear chain reaction. I love this direct comparison because it really highlights the dual nature of rare earths in physics. On one hand, we
we have neutron poisons like europium and gadolinium. These have massive neutron capture cross-sections. They absorb neutrons like a sponge, effectively stopping or controlling a nuclear chain reaction. Think of them as the brakes on a car. On the other hand, we have neutron modifiers, like yttrium. These elements interact with neutrons to moderate their energy without absorbing them. They act more like a traffic cop. This lets the nuclear chain reaction continue safely while providing incredible high-temperature structural stability, which, by the way, was a massive focus for experimental aircraft nuclear reactors back in the 1950s.
And the reason europium is so widely used for nuclear control rods all comes down to this incredible number, 1%. See, when europium captures neutrons, it eventually decays into an entirely different element, gadolinium. Now, if engineers used europium in its divalent state, this decay would cause a massive 30% volume contraction. It would physically destroy the control rod from the inside out. No good. But by strictly using it in its trivalent state, it only experiences a tiny 1% volume contraction when it decays. That completely prevents catastrophic mechanical failure while it's doing its job.
Finally, Part 5, the future of extraction, the green frontier. We've seen their incredible, world-shaping power, but getting rare earths out of the ground has historically been an incredibly toxic process.
For decades, we've relied on brutal chemical solvents to separate these elements, generating massive amounts of toxic and even radioactive waste. The traditional standard is tributyphosphate. It's a harsh organic solvent. And get this, the only reason the industry even adopted it was because its predecessor, hexanone, had a nasty habit of spontaneously catching fire in the laboratory. I mean, we clearly need a better, greener way. Nature, however, has already solved this problem for us using biological strategies. Take phytoremediation, for example. Certain plants, like specific species of ferns, are hyperaccumulators. They literally suck heavy rare earth metals right out of contaminated soil and concentrate them safely in their leaves. Then we have bioleaching, where microorganisms like the Aspergillus niger fungus produce specific organic acids to dissolve rare earths right out of mining tailings or old electronics. These bioleaching mechanisms are just incredibly elegant. Through a process called acidolysis, microbes secrete organic acids that lower the pH and neatly detach the rare earths from solid waste. Then, through complexolysis, their metabolic byproducts act like chemical claws, grabbing the rare earth ions to form soluble complexes that are super easy to wash away and collect. They can even trigger redox reactions to free trapped metals. And the absolute best part? These biological processes offer a highly sustainable way to operate at normal room temperatures without highly flammable corrosive chemicals. It's a process perfectly tailored for recovering rare earths from the electronic waste we throw away every single day. So, I want to leave you with this thought. As we master this biology and start putting these microscopic fungi and robust ferns to work, will the junk drawers in our homes, the ones full of old phones, discarded magnets, and dead batteries, will those become the most valuable, sustainable rare earth mines of the 21st century? It's an incredible shift, right, from the toxic legacy of the past to a beautifully green, biological future.